Hello, it's December 2nd, 2023, Saturday afternoon, Seattle, Washington, from a desk of Ross Finlayson, here to talk some more about descriptive differential dynamics. Those aspects of the theory of mathematics, its subfield called differential analysis, which is part of real analysis, which is part of analysis, which is part of calculus generally, or its methods are called calculi or calculus that I haven't really arrived at anything really new to try to extend yet these ideas that have been coming developed in this theory about here the identity dimension is a very particular way to establish a framing and a framework for models of arithmetic and algebra, not necessarily together, that arrive at some things which make for some notions that for some very usual and regular sorts of systems of equations or differential systems that are the systems of interest here, as they're so parameterized, usually by time, where time is always an available sort of continuous parameter that can be described as an input to any such system which has this continuous milieu. That it serves as the envelope of sorts, a singularity for multiplicity theory, as we've been talking about, singularity theory, a multiplicity theory. A singularity is just a principal branch in a multiplicity theory. For the linear fractional equation and D'Alembert and Clairaut and some of these other usual, often mentioned systems or of these equations that make for why it is just kind of an interesting mathematical device, a tool, something along the lines of what can be formalized to establish for its properties than for what means it provides for the sensibility, fungibility, and tractability, which are kind of the ideas that those are the desiderata and requirements of any kind of theory overall, something that's useful. And then that it also helps to affect a reflection of a deconstruction of what it is in terms of how it is and answering all the other question words about it as these things go. So today, let's see here. I don't really have any new things to say about that yet, and the complex diagram that goes along with it, and then the notions of x squared plus minus 1, and for example, x to the 100th plus minus 1, or x to the 100th minus x to the 50th plus minus 1, and about how then that reflects when x is large or x is small, what that means in terms of the box that it can so live in, about the reflections in those terms, about things that are usual reciprocals, like the logarithm and the exponent, or any of these other kinds of things. There was lots of talk before here about, first of all, the deconstruction of arithmetic and algebra, where they live together in the complete ordered field so neatly that what builds to them in the limit, as it were, or as means of exhaustion, doesn't necessarily so reflect either way that in its construction, both of those things, that they're alike, but they do meet in the middle. And here that's kind of framed in terms of this middle of nowhere. What's available to inductive inference one way results in inductive impasse the other way. And so it's via these methods of deductive inference that is established what are the properties of the space and vis-a-vis the processes, whether it's adding things together and incrementally building them as to an infinity, or from a whole, breaking it down into points, neither one to complete, yet somehow both completing, that inductive inference runs out without arriving at the truth of the matter. The deductive inference makes it so then that it's sound to establish how they do meet. They meet in the middle of nowhere. Not a thing to either one of them, establishing a kind of a third ground. Tertium non datur means the third alternative doesn't exist. It's not on Earth, Yes, true or false. There's no third. It's only true or false. Here it says a matter of about the deductive apparatus makes for a critical approach that it does. And so this is something that is reasonably formalizable, thus it can be acceptable by formalists, conscientious formalists for mathematical rigor, who have that as their general requirement of any kind of acceptable a statement, a theorem, a well-formed formula in this language of objects of mathematics. So those things just kind of carrying along, as we've been discussing here, the deconstructive accounts of arithmetic and deconstructive accounts of the objects of logic, and reconstructive, and synthetic and analytic. Then the theory, the theoria, has that. Well, I've been reading a lot of philosophy, and so in our technical philosophy, we point at two kind of eras: ancient Greeks, and that's split up into various areas, and then the continental philosophy, or from Duns Scotus through the Dark Ages and out beyond that, back into the Enlightenment and Spinoza for his technical sides, besides otherwise his illuminated mysterious things, or as for mystery and such. Descartes, René Descartes, is held up in great regards by pretty much everybody, and Leibniz has these contributions to these touchstones of the philosophy, the monadology. There's a thing in itself, how it is. Kant for having picked that up, and being kind of for being and sign, and then later for Dasein and all that kind of stuff. Then Ding on Sich and the noumenon and phenomenon, having broken that down. So I've been reading some Kant and kind of skip Hegel, but who's still got some things I need to study Hegel some more, because there's something to be said for that, the ethics and morals and stuff associated with Hegel's Locke's done, and all these kinds of people are ignored in terms of mathematical philosophy and the technical philosophy. But there is something about the nihilism and an extension in being and in the study of phenomenology in this. That Kant's sublime was picked up is that there's an infinite and it's real, and so we can not just attain to it, but it's a part of our object sense. That is what thinking beings have. It's an object sense or number sense or word sense. The thing that's different than otherwise the stimulus and response of our phenomenological senses, like taste, touch, smell, hearing, and so on, pain, the electrical sense, or extended vision, or that of with regards to the physical receptors that provide electrical signals to nerves in the usual setting. That this object sense or number sense or word sense all come together to make it so that those are part of both our phenomenological and our noumenological, connected and available. For Kant, we bring that down. We say, Kant, you have an underserved section. It's a definition as a footnote in one of your long extended works. It's called the sublime. So we're going to take that and say that you put that there and left it there for us to fulfill what its place needs to be in a technical philosophy. So that's been kind of what I've been studying a bit. Heidegger then is we add time. And so a continuous domain. So for the mathematics side is like, well, eventually we need a continuous domain. We need real numbers, those which are infinitely divisible, and that reflect the time-like quantity. And you could say that, well, space-like quantities are as well infinitely divisible. In fact, I'd perfectly well agree. And we have theories like atomism, then to superstring theory, and finally to technicolor, and such theories as arrive at how the points of Democritan atomism down to the Planckian regime after Max Planck, and to the trans-Planckian, and from angstroms down to atoms, down to electrons, and then on down to Planck scale, and then beyond to the rough and smooth, the grainy and the aggregate, this continuous things. They're infinitely divisible. So Heidegger is just associated with that with time. And then otherwise he just translates the Eleatics, the ancienter Greeks, the more ancient Greeks, the Eleatics, and then Socrates and Plato and Aristotle. And then there's a student of Heidegger, Gadamer, if I'm pronouncing that correctly, And so he basically picks that up and establishes that the result of the continental philosophy technically is a Platonism. So that's that these things exist then beyond the noumenon. All the mathematical objects are enduring, eternal, real, and available to any creature with an object sense and number sense after word sense, qualitative and the quantitative. So that's the thing. So for the differential side of it, then what I've been trying to consider is, again, the inverse of meters per second, or distance per time. That's time per distance. And then similarly, these higher orders of changes in position over time, or time over position, vis-a-vis that the higher orders are in the units of the higher powers of time, vis-a-vis then when they're in the higher powers of distance. So that space and time are these two complementary quantities that together make space-time, that in the continuum of objects, space-time, everything is in somehow. It's capitalized, usually called space-time for Minkowski and space-time and all its contents after Einstein and stuff like that. And then for things like scattering and tunneling theory, or the unified field theories and such, that the field is just space and it's in time, and it's generally considered that is utterly available to the phenomenological in all means of mesoscale, in the middle, micro, macro, meso, the mesoscale measurement. And what that means with regards to what can then be established as the reproducibility of experiment. So that then when there's a notion of some kind of outlay of an experimental apparatus, its configuration, that's kind of the thing it is. So here for this differential analysis, then what I've been trying to figure out is how to frame these duals, these complements, these inverses, position over time or time over position, to help reflect that there are different numerical methods to arrive at either in each, and then that also in the philosophical context of a theory of logical objects, of a theory of mathematical objects, a theory of physical objects, they're models, that we have physical and mathematical interpretations of these things, that's how it's arrived at soundly, a theory for this notion, not quite of like the theoria or whatsoever, the idea of, seeing the mind of the deity or something like that, though that it kind of is, where it was so that science is the great illuminator in a sense of providing all these things that were available to the phenomenological, and then that it need not be accepted science for its own sake, the argument from authority, coherent, pragmatic theory of truth, that there can still be just a real theory of truth, and that it can be unfalsifiable and super scientific. What are its real attachments to not just reality, but any such matter of the philosophy or the logoi, the logos of reality, but that also that science writ large in its argument from authority can be tested, that its falsifiability, that experiments can be reproduced, and models and theorems can be falsified. Then that for statistics, it's just kind of follows from that, is like even with less data than that, we can establish hypotheses statistically, and then given various statistical gatherings of data, or the sampling, for this sampling, observer, and measurement effects, where sampling is kind of like gathering one value, measurement is gathering a value in a unit, and observation is gathering a value in units over time. Sampling, measurement, observer effects, that these make for pretty much the usual, or a usual, philosophy of science, and how that was arrived at, that we point to on our entire canon of that vis-a-vis such a self-contained description as this, which would also suffice, if not necessarily providing enough of the context for the reproducibility of the experiment of considering the surrounds and milieu itself, there would be so a thing. So in this manner, I feel that it's kind of enriching. It's an enrichment, compared to a usual curriculum, what might just be, say, here's some tools, you learn how to use them. They'll be here when you get back, That it's, here's some tools, and they are eternal. So you won't have too much to remember, because whenever you rethink them, they're kind of the same in an eternal growing thing. So that's the usual sort of reverie, which is usual reference to dreams, the dreaming state of things, vis-a-vis the deliberate ponderance of things, and these kinds of notions. So let's see here. I did find some books here in a stack, so I'm going to just kind of leaf through them a bit here as kind of looking through them. See here. Quantum field theory and curved space-time. This is by a fellow named Robert Wald, and he's talking about Klein-Gordon. You might hear of like Klebsch-Gordon and Klein-Gordon after Kaluza-Klein, and for Yang-Mills and Yukawa potentials. This is for field theory and other usual things. Quite a bit that goes on in terms of the higher order and the multipole moments of the establishment of here. Talk about Hilbert space and Minkowski and Hilbert space and how those things are in terms of Borel spaces and otherwise linear spaces, quite usually most familiar as R cubed, the real space Euclidean of 3 dimensions with the attachment of a Cartesian basis or origin and an orthonormal vector basis in here, of which I have attached furthermore an identity dimension rising from that as a ray in all dimensions. That space of states, who's talking about states, particles, and general curved space-time, which is flat. That the curvature of space-time is as with regards to any differences in the metrics and the norms from having everywhere straight lines and right angles with regards to what gains tension and then relaxes. Tension and then relaxes. These are the kinds of things that go into its definition. Stationarity. There's unitarity, and the unitarity is a very high-level concept that things are symmetrical everywhere, that the laws are the same everywhere. Thus, in our universe, serious difficulties would arise if we attempt to define a meaningful notion of particles whose wavelength is larger than the Hubble radius. Well, particles, as a conceit like to points, they run out. Kind of as was begun here talking about the deductive inference, that in this sense, we have to have these models of continuous domains, and they're not always interchangeable, whereas they kind of reflect on the same continuity. Line reals, those like Aristotle's points in a line, contiguous beads on a string. Yeah, I know they're not standard, and we talk them away in pre-calculus, and we only talk about the complete ordered field reals, and then sigma reals, and that these notions of the continuity and measure theory and invariance theory today kind of have things going on in the quasi-invariant for these complete metrizing ultrafilters, which are these things to help represent like so. But as a practical matter, there is little difficulty employing a particle concept in most other circumstances. Well, I mean, it's a matter of divisibility and the notion of reaching kind of a floor on divisibility. And then statistical mechanics and the statistical ensemble are meant to build that up. And then all such matters as that of the discrete and the normalized are about how we block infinities out of mathematics insofar as when we only have this inductive side to build off of, the scaffold is very regular and usual and standard and fully available to phenomenological physicists in his philosophical side, like Einstein put it in the talks on the Einstein's Out of My Later Years, one of his greatest works, if you only read it for the physics parts, and you're welcome to take or leave his more personal asides aside. That he left it neat. While some readers familiar with standard presentations of quantum field theory and flat spacetime might be disturbed by the lack of a notion of particles in curved spacetime, because they would stretch and they wouldn't be dimensionless, We have taken great care to emphasize here that it should not be cause of alarm, since the notion of particles plays no essential role in the formulation of quantum field theory. I will not necessarily accept that, except that the idea is that the field number formalism and quantum numbers in the field normal formalism of quantum field theory are particles and waves, or the wave packet, solitons, instantons. They're defined variously many things with the association then of their surrounds. The gauge, the torsion of the metrics and the norms that define whether the space around them is ordinary, it's orthogonal, it's vector basis from any given perspective. Matters of perspective and projection. So. Readers familiar only with presentations of special relativity based upon the use of global inertial coordinates might well find this fact to be alarming. Well, they should. They're totally ignorant of it. So yeah, what this really gets into is a bunch of the different notions of different ideas of a space and time, space-time, and the curvature, and goes in it. And here he's talking about black hole thermodynamics. So a singularity is in this gravitational singularity is usually considered to be a black hole. And when we were children, there was a movie from Disney, I guess, and it was like about a black hole. So there was a space station that was floating right outside the horizon of this black hole, and so that was just like everything would fall into it or whatever. And I forget what happens in it, but somehow they were able to stand on the deck there and kind of observe it, and then it fell in or something like that. I forget how it began or ends, but I just remember there was just a scene or two from that movie. I forget what it's called, but it was an introduction to the physics of such a thing by its description and definition at the time, which was new to most people who would not have been the students of such this theory. After Chandrasekhar was a great physicist who established the laws of the values. And so you got the Schwarzschild radius, and for Chandrasekhar, it's like how small would it be when the radius and the density would combine to make it so that the force of gravity, according to this model of the pull gravity, would not allow anything to escape. And so we have Chandrasekhar and Schwarzschild. And then there's here, for example, Kerr and Kresgeles and turtle coordinates. What are the coordinates of the gauge or the metrics and norms of those things that surround it that define the geometries that result back from these highly nonlinear systems back to something that's linear, that these different coordinate settings just reflect something that when you add them back up, you can paste them together as linear, when in fact the systems they're modeling are highly nonlinear, relativistically dynamic and such. And then Wald, for example, this is Earman and Wald. So Earman, Stachel, and Corcoran they each had the first name John, and so they're three philosophers of physics that are pretty famous in the United States, out of Pennsylvania or something like that. Stachel and Earman here, and Corcoran, for Corcoran's axiomless natural deduction, and Stachel and his very well reasoned writings, and here Earman on singularities and how are they not paradoxes in space-time, besides the fact that mathematically that division by zero is prohibito. Cosmic censorship he talks about, these being various things where the engineers and the scientists and the physicists and their philosophers, they would set up a thought experiment in this Gedanke and this Ansatze, and they'd set it up in this great scaffold and this perfect world, and everything fell together and lines up great, and then they point to the edge and it points back in them and says, "You're wrong, can't be right." So they call it cosmic censorship, whether or not there's a naked singularity, that a naked singularity would be raw in the sense, in effect like an infinite value. Just like when you try to divide something infinitely small and give it a finite value and add all those back up to analytical character things, why wouldn't that add it back to infinity? Well, because it's just an infinitely small ratio that only over that grows to a finite bounded thing. That this is the kinds of things that go into the Big Bang and the horizon problem. We talk about time travel and the lack thereof. There is time travel. It's always forward. There are no closed time-like curves. at all. Time slows or joins. This is a usual way to have that there are singularities and for multiplicity theory and the dynamics beyond the regimes out to the running constants, whereas time reversibility after charge, parity, and time, CPT, the time is the only time reversibility is the only thing that's never been falsified or let out. So according to science writ large today, there is no backwards time travel. No. Now, you could throw something in a black hole, or it could split and have two images on either side, inside or outside a black hole. And inside the black hole, it could live in eternity. And it could have its own copy of all its contents and stuff. So if it never met again, it could have a totally different outcomes, two different worlds. Then as to whether they could rejoin, it's only like time would have only slowed from one or the other to come back together. So these are kinds of usual things that get into usual things, and that science still hasn't found a paradox. That particle wave duality and resonance theory and stuff like that just gets richer, more super fluid, super classical. Fritz London's notions largely, who is relevant for bringing some of these things to physics already. Fritz London is a very, very great mathematician and scientist. The two most fundamental theories of 20th century physics, quantum mechanics, a particle model after atomism of what's essentially the infinitely small or the utterly smooth particles for the quantum, and then the behavior of these things as particles and waves, their duality, and the general theory of relativity stand in wary regard of one another. Each is spectacularly successful in its own domain of application, both in making accurate predictions, providing conceptual understanding of otherwise puzzling phenomena. In the latter achievements lie the roots of what is arguably the most important challenge of contemporary physics. It's hard to see how any future theory that incorporates the successes of both QM and GTR can dispense with the conceptual apparatus of either. Well, you just need to make each one richer to where they come back together. Then for gravity, it's just in the middle. It's a fall gravity. That Solomon Weinberg's asymptotic freedom and the 70s for quark physics and gluon physics make for Technicolor all the way down and this kind of thing. That fall gravity is real. Science is coming up to this. But combining them into a unified quantum theory of gravity has proved to be formidable and is thus far unfulfilled. That's fair because it needs mathematics beyond these regular regimes to establish for the highly nonlinear what happens when two continuums break or have the doubling space and doubling measure. These days it's talked about doubling spaces and doubling measures because there's been an investigation in mathematics, and that one of the most beautiful facts of mathematics is that if you take a unit line segment and split it up into points and put them back together, it doubles. It's kind of like the Banach-Tarski paradox, but it belongs to geometry instead of the algebraists who talk about it in words, because it's really the mathematical objects themselves. So that is that would be news to most people. That would demand its own entire formalism. It would demand an entire theory to explain how formally and reliably and logically that could be so. Despite their successes, QM and GTR are beset by problems that raise worries about the foundations of these theories. QM by the measurement problem and associated problems of non-locality. Here we talk about resonance theory. It's not that big a problem. It's just super classical in the sense that there's space contraction, length contraction, and time dilation together, space contraction. GTR by the problems that are the focus of this study. So here he's just talking about singularities and beyond the regime of the usual linear things that affect that in ratio that they are the same to any given scale. They're beyond scale. They're out of scale. It's not a problem that they go off to infinity. In fact, it's a good thing. And then figuring out via deduction about the points in the space, or point in the spaces, how there's this middle of nowhere, and inductive inference arrives both ways to this meeting in the middle, helps to explain how there can be things that belie the finite inputs and still work out. Or about half, it's like, well, is it 0 or 1? Well, it's about half. So these little amusements I have from these things have amused me for a long, long time. I really do. They find them. These are beautiful things for me for my mathematics study, because not many people really know them or get them. I had to kind of draw them out myself. I have a big pile of these things that I've been hoarding these things. On the other hand, the challenge can be seen not as calling forth new physics, but rather a new understanding of quantum ontology and the ways in which Hilbert's space apparatus of the theory relates to that ontology. Reactions to this way of reading the challenge range from new interpretation rules for assigning values to quantum observables, or the space that they're in. Even when the state vector of the system is not an eigenstate of the operator corresponding to the observable, linear, to a world picture not in, like Borges' garden of forking paths, many worlds interpretation, no. MWI is prohibito. There's only one universe. That's just a fallacy after it's like, it's stochastic. It must run out into functional freedom. It's like, no, it's not stochastic. It's just super quantum or what? This kind of thing. The wave function collapse is real. Vis-a-vis that the frequency of it is so high, simply, that sampling is essentially the same thing as seeing random things. That quantum theory's association with the stochastic or random is just because it's just another sampling scenario, just like anything else. And you build a picture of it from what samples and measurements and observations come into effect. Statistical. That doesn't mean that the background is digital. It means, again, that it's continuous and analog. So, and then Borges was a great philosopher and a novelist, and he wrote things like the Infinite Hall of Mirrors. But that's a nice place to visit. It's a place of the imponderables, ponderance of the imponderables. So yeah, that's right out. There's the quantum consciousness bit could be a thing because there could be basically entangled states of any two objects that have ever met, which if there's a Big Bang theory, everything would have met at one point and all come down from it. That it is possible to say it's all part of one equation. It's just that usually any such effect would be so entirely attenuated down to nothing that such notions of ESP or the quantum consciousness or telepathy are pseudo-scientific in a sense, while at the same time it's not to be said that it's scientific to say they don't exist because they're extra locality. Or if Einstein has like, well, God does not roll dice, and action at distance is spooky. It's like, well, God just rolled one dice and it's still rolling, and it would be considered spooky if you didn't know how it so arrived. Like the mechanical Turk, it's like hundreds of years ago or whenever it was, somebody invented a mechanical chess machine, a brain mechanically. Well, they just hit a guy in this box and he did it. So if you knew that, it wouldn't be so spooky, vis-a-vis something like the formalization of knowledge and thinking and how it so results as things. Reflections here are a little off, but let's see. Yeah, that's about the same. So talk about Einstein, the perihelion of Mercury, and here we talk about Fresnel too, and that there's that's about half right, but half was close enough when before it was just off. He's like, well, now it's only half off. If you know these things. Schwarzschild produced the exact solution of units alpha equals 2m, Schwarzschild radius, r equals 2m. One naturally wonders about the meaning of the non-regular points r equals 0 and r equals alpha. They're called the horizon and the origin. And it's generally considered that, well, all singularities gravitationally must be perfectly spherical. They're not. You can imagine a black hole that nothing could ever exit it because it's so strong and hungry that anything goes onto it just adds to its mass, and it would still only grow so much as its mass. But you can also imagine, say, two large stars or objects in space. And so out in space is the biggest laboratory for this, is the cosmology and the cosmological survey, because then they can find binary pulsars, dual neutron stars, and other such things that exhibit relativistic dynamics, largely vis-a-vis their rotational relativistic mass. So they could create in the center of them an oscillating center of mass, and at one particular moment in time that could coincide that it makes a singularity inside it gravitationally. But due to the oscillation, it could fall back out. And so when you get to stuff like Hawking radiation and stuff, it's like, well, can anything ever come out of a black hole? It's like, well, if you just think about it like a swinging pendulum, you can pretty much mesmerize yourself to imagine it like so. So keeping things simple is along these lines. Otherwise, perfectly spherical, perfectly Euclidean. The idea being that all this stuff then ends up being for Einstein and is how you have to compute the differential system's behavior over time, or is according to Einstein, it's all just a differential system, physics and space-time and all that. That it's kind of like so that this is spherical, but Fritz Zwicky's idea that everything is spherical is naive at best. But it facilitates some usual things. That otherwise any two things in the space-time kind of adjust. They each have their own perspectives and projections. So a lot of times when you talk about the metrics and the norms and anything to do with their coordinate settings, that relativity is coordinate free. Well, that's because it has to build in the corrections to these coordinates with whatever makes them come back together and be smooth and continuous. That's just the way it is. And so that's usually then just broken down as like, we are doing boost addition as a number of vectors added together in a highly controlled environment like a linear accelerator or something like that. And that works well enough to give fine numbers for things like the design of circuits and stuff, and the absolute guarantees as far as the process goes to understanding, according to the statistical ensemble and the statistical mechanics that is the rule for physics today, like thermodynamics and Leonard Weichart, flows of things, flows of discrete particles and things across continuous areas, and their measurements, sampling, and observation. This is the usual thing. Talks about de Sitter and anti-de Sitter. So de Sitter space is kind of like there's no torsion between it, but somehow it just kind of bends and wends its way through it. And anti-de Sitter space is kind of, it goes through it and then it's like entirely inverted and come back around. So in anti-de Sitter space, you can just basically say, oh, I can wave the needle however I want. So whenever I hear anti-de Sitter space, I'm like, that's off the deep end there. You need to have it from both sides if you're going to be talking about something that's de Sitter space. De Sitter space is pretty close to Euclidean space after torsion, Rindler, rotor relativity, these kinds of things, compared to negative time or some other really imaginary quantities that don't have any physical interpretation in the mathematical model or mathematical interpretation in the physical model. except insofar as they're placeholders for otherwise. Then it's perfectly suitable to establish that conceit of why these things are reflecting as numerical values or the numbers, that they're not real numbers associated with these things. That it's just an entirely different scratch pad to write things down on it. That's all it is. Integral from 0 to pi halves, or that would be, or theta over 2 here. That would usually be part of 90-degree rotation, is what that reflects, or where theta equals pi. I mean, if that means anything, it doesn't really. But here it's about ds squared, that being the metric. It's like, well, we have the square, and it's our definition of right angle and straight lines as far as this point goes. It's the metric. It varies. According to that, then, at any given point in time, everything you can compute its instantaneous velocity, and its instantaneous velocity reflects what is this motion along the geodesy according to its metric. That's all. And it's just a differential squared. Leibniz and Newton had a great dispute about priority. So Newton kind of approached things as from the fluxions and the differential, f dot, x dot, these kinds of things. X prime, that's the notation. And Leibniz also approached it from these differentials as raw, the differential, dx, and then also the integral bar, which is kind of an extended s for summation. Just like it's the sigma of the deltas, sum of the differences, it's the summation of the differentials, the sum of the differentials. Integration, mensuration, computing a measure, computing an area. These are the things. Why would it, when it goes into like s ds squared, and it's a raw differential that small, and then when does it make sense you can treat that as an algebraic quantity? So way earlier in these talks, we were talking about the notions of quantities. And this comes from the talks about the Mogan and the electromechanical effects and applications in his development of a nonlinear rank ordering builder according to piezoelectric and various things, how he could provide such notions as a surface acoustic wave transducer. Anyways, the ds squared of the delta and the raw differential can and can't be treated as an algebraic quantity by itself. And so it's usually to be let out that it only reflects itself truly when it's in as a ratio. So all the variables are considered in the thing. Could it be that Einstein was applying his 1918 definition of singularity and making the same mistake that Hilbert made in 1917? Einstein qualified his conclusion that a singularity exists at r equals pi r radius over 2 with an until further notice clause. An unnecessary concession of Hilbert's restriction on the nature of the coordinate transformation needed to remove the singularity had been in effect. So this is why these books about space-time continuity and curvature in the large over history have a lot going on with them, both for physics and mathematics, that mathematics needs to provide this. Physics is without a paddle, as it were, if it doesn't have a way to formalize these notions quantifiably, mathematically. So the mathematics must provide it, is that somehow it does. So it'll remain to be seen how that goes. All right, let's see. Eric Temple Bell's Men of Mathematics. So if you haven't read Eric Temple Bell's Men of Mathematics, it is after Matson Weaver, History of Mathematics, History of Physics, and Carl Boyer's The Conceptual Development of the Calculus, History, and also his History of the Rainbow. That's a great history. The Eric Temple Bell's is kind of got a through a lens, a history of the French geometers and algebraists after Bernoulli's, into the Lagrange and Laplace and these guys, and after Descartes and Leibniz and such, and then into and about Pascal and Galois, and I kind of relate Pascal and Galois kind of the same, although Pascal had a lot of real insights into the binomial theorem, Pascal's triangle, and all that stuff that works out by showing that, well, you can just add these things together and it works out the same as you multiply them together, like the x squared plus minus 1 bit in either side in the polynomial and the binomial. Whereas Galois was kind of like, I have seen algebra and it is a group. And it's like, that is a perfectly clear abstraction. Call that group theory and say it's a Galois group. It's kind of when the algebra broke from geometry, in a sense. And it makes lots of things lots easier, and it makes lots of things lots tractable, but it doesn't necessarily guarantee you can ever get back to the geometry side without pulling that back to. But they don't have to disagree, and that's why when you look at something like Vitali's doubling space, and for measure theory, then what for algebra is the non-measurable, but for geometry is the doubling space. And for Banach-Tarski, that when you have like Miselski or the formalization of the Banach-Tarski paradox that's built up in algebra, and then it's kind of like, things just kind of come back together in the sorts of these words that would have to define them. It would take twice as much to so define it. Whereas in geometry's sake, it's like the act of such a notion would be, according to the Banach-Tarski paradox, where a solid ball can be broken into 4 or 5 pieces, everywhere non-continuous, and then those two either side assembled that would naturally fill the same volume. At first, there's Vitali's line segment. He cuts it into infinitesimals, reassembles it, make one in length 2. Then there's Banach-Tarski's. He takes a ball, he divides it into 4 pieces, maybe 5, if one of them includes the point at either pole. Those two, either side, double. It's a doubling space or doubling measure. Geometry and algebra have this either way. So then here when I'm talking about arithmetic and algebra being deconstructed, it's kind of attached, and geometry's points to the arithmetic and algebra's to, after the theory of Galois and abstract algebra, Galois. So that's kind of what's going on here. Then it kind of ends with Poincaré. And so Poincaré, and this would be after Cauchy and Weierstrass, and after Dedekind, talks about Cantor, and then after Dirichlet, Poincaré is kind of held up as the greatest of these abstract geometers with regards to analytical character and this non-standard stuff that is just outside the milieu of what in here in this differential dynamics or descriptive differential dynamics is built up for function theory. That we have Poincaré's rough plane as for Euclid's smooth plane. And then as for Dirichlet problem and the everywhere discontinuous yet still of the analytical character that's related to Vitali and doubling or having, middle of nowhere. Borel versus combinatorics, as I put it, when I found that Borel and finite combinatorics would find each other at odds, one saying almost everywhere, one saying almost nowhere. How that somehow between them, it's halfway, between 0 and 1, what otherwise is the middle of nowhere. That induction either side, you might as well say, you've never made it to 1 from 0, or you've never made it to 0 from 1. That's why axioms natural deduction, as for example, out of the square of opposition and the dialectic and the Platonism, are very strong. And for some, universal, and truth and all that kind of stuff. Truths, immutable necessary truths. Veritable essence of all material things. That took over 2,000 years to knock the eternal truth out of geometry, and Lobachevsky did it. Here he's talking about non-Euclidean geometry, which are just ways of taking nonlinear things and mapping them to, Euclidean geometry. I mean, there are topologies that are quite unrelated to geometry's topologies, which has quite a handful. Geometry has more than one topology, which means to describe a neighborhood and proximity of points that according to how points are defined, that they come back together. So Raymond's geometry and Lobachevsky's geometry, Sierpinski being basically that part to the word-based or algebraic topologies, particularly. The otherwise, space-time is, flat, straight, and there are straight lines and right angles, vis-a-vis that there's curvature and torsion in these coordinate settings, and they come back together in the establishment of when things change and when things rest, So Eric Temple Bell is to be read with a sort of grain of salt from about, that it was about 100 years ago, and some of the conceptions were a little bit different. And he's quite valuable and ebullient. So he's enjoyable to read. Let's talk about Jacobi and Fourier, and what's he got here? Galois. Then he gets into Galois, who had a tragically short or brief life, for having a few years at school and kind of stamping this theory of the Galois group as kind of fundamental. And here that's been broken down via deconstructive accounts to when they do and don't hold. It's not the ring that kind of brings them all together. It's more just kind of the lens that you can see both sides through, or something like that. Galois' Death in a Duel. To Cayley and Sylvester. So that gets into, if you like complex numbers, how about some more? Here we talked about that in terms of the complex diagram up after the identity dimension. How about less? There are many ways to build out these extensions to the imaginary numbers or placeholder numbers of these non-principal roots or non-principal branches of otherwise roots and powers. Or here is it brought up: increment and addition, multiplication powers, exponent and tetration. These kinds of things coming out with division and that coming back down. Two primary things together, a gestalt, that kind of come together. That Cayley and Sylvester were pretty great, and they have clear ways to show how algebra works through these things. Riemann, Christoffel, Ricci, Levi-Civita, Lee, and Einstein, who provided Einstein a lot of his backing. He was able to take all this stuff that had just been invented 75 years before and say, this just kind of fills the gaps, But Einstein is still pretty much a hero. Desargues, Pascal, and Poncelet, the Pythagorean propositions. Lindemann's proof, Hermite and Lindemann. So Eric Temple Bell is the man of mathematics, and it's not to be not inclusive, it's just kind of the people of mathematics, Kronecker, Werner, Kummer. These are each associated with particular results, kind of associated with them. Where all we really need are Cauchy and Weierstrass and Riemann, and then you can add Lebesgue and Stachel on top of that, and you can have real analysis like so. But that's just this, the regular linear standard curriculum. That there's this stuff like Poincaré's and Dirichlet's are about the first things that got above that's recorded and so brought in. So even after all the stuff that arrived, like what Thomas Hardy calls pure mathematics, and he associates it with geometry and Euclidean geometry, Dirichlet and Poincaré are above them. And Riemann is he's all right. Euler and Gauss have a lot going on, and but a lot of it is just kind of their own private playground of after complex analysis. after lots of treatments on the geometric series. So Euler and Gauss are, of course, great. And so this is from reading Eric Temple Bell's The Metamathematics, you really learn a lot about who knows what. So, and this other book here is Willard Van Orman Quine's Set Theory and Its Logic. I found this great book by Suzanne Langer. It's an introduction to logic. If you ever need a college level textbook for logic, I would recommend that Langer's Logic. So it is at once elucidatory, and it covers all the stuff that came out of Russell and Whitehead and up into Quine after Frege with class set distinction and the new classical logic, which is not really classical nor necessarily is it logic. The Boole's after De Morgan's, Augustus De Morgan's, who's basically the most important thing in logic is to know Augustus De Morgan's rules backwards and forwards. So you got to know your P's and Q's, and what that is Augustus De Morgan's rules backwards and forwards. And then Langer's book is great because it at once illustrates and goes through all the necessary things to know all those things, but it also makes sure that it talks about that there's the predicate calculus that's more important than propositions, and then there's the theory of relations, which is more primary than predicates, and then that it helps introduces a class set distinction, and it puts down material implication and this kind of thing. So yeah, that's probably the best course for an introduction to mathematical logic. Not quite mathematics, not quite logic. It has to be both mathematical logic. Suzanne Langer's book. So Quine is pretty great because then he lives in an era after De Morgan and Boole and after Frege and after Bertrand Russell, who came up with they basically just deal with stuff like x equals not x contains not x, or x not contains x, in terms of that being the sole relation of a very, very primitive theory called set theory. There's only one relation, L, that these are the objects and everything is built up on top of them. You introduce a constant named 0, it's an empty set. You introduce, according to Russell here later, a constant named omega, it's an infinite thing that somehow doesn't have the problems of the infinite. That what Russell did was he took Frege's theory otherwise of all this regular ordinary stuff for finite combinatorics, and a perfectly suitable simple grounding for such manners of bean counting or anything like that. Frege's Begriffsschrift or whatever it is, the Grundgesetze. And then he said, oh, well, look, I got a paradox because I framed this as a matter of quantification, x not contain itself, and the set of all sets that doesn't contain itself thus does, thus that it would be a inconsistent multiplicity. And Frege was like, I give up, And so Russell said, well, fine, then I'm glad to have done that. Now I will just make one and say I defined it away. And why didn't Frege say, well, I just define it away? Isn't Russell a hypocrite? I think so. Class set distinction is a thing, yes. It's also not a thing. But anyway, so Quine came after that. And at the same time as like Alfred North Whitehead was the other guy who with Bertrand Russell said, oh, in Principia Mathematica, we're going to prove that 1 + 1 = 2. I was like, it doesn't take that much to get that figured out. There are many, 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 many ways to do that. Vis-a-vis the formal axiomatic apparatus that he arrived at to get there, has some opinions, and they're great, and they make regular ordinary theory, and then today that's all enshrined, and it's proper, and its canon is called Zermelo-Fraenkel set theory, with the important bulwark of works about uncountability from Jörg Kanner, and how that makes a formalization for a rigorous standard subset of real analysis. So anyways, Quine, where Quine was an American then, so all that was kind of continental or European before. And then Quine, he, first of all, in this book, he addresses those options, those alternatives, those opinions that one need not share of Russell to arrive at objects of logic. And then he also develops like a real numbers, and so he kind of comes down from the real numbers as wholes instead of parts, and then he just does that to kind of be different. He's like, well, I found a different way to do this, so I'm just going to call mine this, and that way otherwise reading his book would just be same as recounting the previous book, recounting the previous book, recounting the previous book. Kind of like as was discussed earlier, it's like, well, what Gadamer says is what Plato says. He says amicus Plato. It's all been done before, kind of a thing. But anyways, then also later in terms of his book, at least he introduces the concepts of that an inconsistent multiplicity maybe is a real thing, and what it is not inconsistent, but reflects this sublime of Kant's. This is why we need to find something in the canon that would allow this to be dogmatic. Is these words of Kant, the sublime, and for Quine, the atom of Quine. Anyway, so for differential analysis, then there's a whole sort of a history and a formalism. Then that for the foundation and the formalism of these things, there's these notions of continuous domains. It's definitely central for objects of mathematics that they include continuous domains primarily, fundamentally, elementarily. Then with regards to how this will carry out in terms of the quasi-invariant and measure theory, Ramsey theory, and the doubling spaces and doubling measures that so arrive in the coincidence with notions of measurability and non-measurable, and the revitalization of measure theory. That these are the kinds of things that then again we'll get back up to for our primary consideration for differential systems, the behavior of observable systems over time, differential systems, and then particularly then as well the those systems that are defined by their own behavior, or so that would regress to the mean, or that would otherwise exhibit organization, the opposite of entropy. Entropy is kind of poorly defined, but entropy. Enthalpy, extropy. That time carries on. Yeah. So hey, have a great day. I shall so hope this finds you well and in good spirits and health. Season's greetings. This is a pretty far north place, so it gets to sunset soon this afternoon. Well, so long.